We're Capstone Team 1, and our task is creating a drone detection and tracking system for the Tennessee Tech Campus Police. The members of this Capstone team are Meredith Nye, Abe Perkins, Sloan, Stewart, JieJun Stowell, and Austin Williams. So first off, I'm going to start with introducing and formulating the problem. So unmanned aircraft systems, also known as UASs, or more colloquially known as drones, have been gaining popularity in more recent years, with more people flying them and them becoming more of a safety concern because of their abilities to record things remotely from high up, and they're easy to fly around. So the Federal Aviation Administration, or the FAA, has created a remote ID mandate. So all drones that are 250 grams or more must emit a remote ID signal every second, and this remote ID signal carries information such as the serial number, the latitude, longitude, location of the drone, the altitude, velocity, and the location of the control station, etc. This is the most important information for our purposes today, um, and for the drone detection system. So we're going to receive that information and store it into a database and have a website so that the Tennessee Tech Campus Police are going to be able to interface tracking with the drone, knowing what drones are on campus, what drones have been on campus, and what drones are allowed to be on campus and what drones are not allowed to be on campus. So to do this, the systems we need are going to require our receiver subsystem, a camera hardware subsystem, and camera software subsystem to take a picture of the drone and or control station as it's on the contiguous campus, power, a database subsystem, and a website subsystem. So first off, I'm going to talk about the receiver functionality and constraints. This is my subsystem. So the purpose of the receiver is to pick up the remote ID signal and send the signal to the database to be stored. So first off, I want to talk about the constraints, and this first constraint is a design constraint. It's the frequency band constraint. So the remote ID signal has to emit either a 2.4 gigahertz frequency in the Bluetooth or Wi-Fi. Okay. Now there's a third emission, and this is the 5.8 gigahertz Wi-Fi. We're going to ignore that emission because it is an optional emission, and if it is being emitted, then the Wi-Fi must be emitted as well. It cannot come out on its own. We're doing this because the range, we would have to increase the amount of receivers we have to be able to pick up the signal because its range is it's not going to go as far. The signal is not going to travel as far, so we're going to need more receivers to cover more area so we can pick up that signal. When the 2.4 is already going to go further anyway, and that one has to be emitted. So a design constraint or an ethical constraint is ignoring other signals. So any other signals that may be out and about that the receiver would normally be able to pick up, it is going to ignore. It's going to ignore these signals due to privacy concerns because Tennessee Tech does not have a right to be storing data and picking it up regarding anything besides the remote ID signal. That is the only purpose of this system, so it is not going to pick up any other signals, and drones that do not emit remote ID signals are going to be out of scope. So it also needs to receive all of the RID information. So by picking up all of the RID information, it's going to be able to get all the meat and potatoes that we need and This has to happen so we can know where the drone is, we can properly map it, and all the other subsystems need this information. All the other subsystems need, besides power, need this function to work. So the next constraint is that all of the receivers need to be able to cover the contiguous campus, and this is the main land of campus that is unbroken by and disconnected by roads. So Tech Village will not count. This is just the main area of campus covering from the RUC all the way down to the FIT and the gravel lot. Now, the receivers need to have a minimum reception range, so we're going to be able to cover this campus. And right now, based on the Bluetooth online calculator, the the current receiver is spec'd out to be able to pick up signals from about 174 meters away, at least 241 at most. So by using the minimum range and using a map to cover this radius and put the receivers in possible places, we have detailed that we need about 9 of these receivers to be able to cover the full contiguous campus, and 20 meters off of the contiguous campus, so that the Tennessee Tech police are going to more easily be able to follow where the drone may have gone or started from if it comes from off campus. Now, if the drone comes from off campus, the control station will still be given the location of to the receivers, so Tennessee Tech Police will still be able to know where the drone controller is. Okay. Now, the way we're going to do this is the way we're going to receive the signal is we're going to use the Arduino Nano ESP32, and this uses a ESP32 Wi-Fi and Bluetooth module to pick up Wi-Fi and Bluetooth signals, and so it's going to be able to pick up the RID signal, and then we're going to use Python to encode it onto the microcontroller to send the Wi-Fi or send the data over the network to the database subsystem. And to do this, we're going to be using an ESP82, another ESP32 to stay connected to the Wi-Fi permanently, so that when it picks up a signal, it's going to immediately be able to send it to the database. That is it for currently. The subsystem has not been signed off, and so no parts have been ordered, but that is all for my subsystem, and I'm going to pass it off to Aaron.
Hello, my name is Aaron Stewart, and I am presenting for Group 1 of the Capstone drone tracking system. So to cover the system, to start off, the hardware system is responsible for the design and implementation of a hardware system to track and capture an image of the drone as it's flying in the air. And so that can either be the drone itself or the control station. To move on. So this is going to be a two-part system, whereas I'm covering the hardware component. My teammate, Meredith Nye, is covering the software component, so she will be controlling what I design, and I will be designing things so that she can control the image capture of the drone. And so it will track and photograph a UAS as it flies across the sky, and it will take multiple photographs of it to ensure that the image is clear and that we get a good image and we get a good picture of it before it flies out of frame. It will also track and photograph the UAS's control station where it's applicable, because if it's closer, it's easier to get a picture of the person itself controlling the drone rather than the drone itself. That will help police when it comes to collecting evidence for repeat offenders and also stopping new offenders. And once it takes these photos, it will send those images to the database and will send it over the Wi-Fi protocol. The processor, which we'll cover in a second, has innate Wi-Fi capabilities. So it will connect to the database's microprocessor It will transmit data across that, and the database will use it however it sees fit for the website itself to use. So the database will handle this data storage for all subsystems, including mine, the software system, and the receiver system, and the website. And it's also in the data that we send out will be packaged and parsed by the software side of the camera system. And so to go into details, the microcontroller or processor that we're going to be using today, or for this project, is the Raspberry Pi 4B. It is a 2.4 gigahertz 4-core ARM processor with 8 gigabytes of RAM. It's capable of hosting both Linux, Windows, and Mac if you choose to do so, or you can just run on the innate Raspberry Pi OS. And it's capable of programming in both Python and C++, depending on what you need for your application. So it's for this process, we're going to be using OpenCV for the camera module control, which that'll be covered at a later time. Peripheral communications can also be handled over the USB protocol. That can be set up through the Raspberry Pi software or through Linux or Windows or what have you, whatever you want to set up. And there's also 16 GPIO pins, which stands for General Purpose Input Output. And you can use those for your hardware controls, for sensors, for motors, for pretty much anything your heart desires, as long as it can be controlled by a digital pin or analog pin. For the camera, I've chosen to use the ELP 8 megapixel USB 3.0 camera. This camera is also using the Sony IMX 317 image sensor. This camera comes with a telephoto lens with a 2.8 to 12 millimeter focal length. And once you put all the numbers together and do the math, it comes out to about 4 times zoom rating. So you can zoom up to 4 times its normal focal length. And the manufacturer did not specify the field of view as it changes with the zoom level. So we will have to do a little bit of testing to determine an exact number, and it will that'll come into play later on in the presentation. As for manual adjustment for the zoom, the focus, and the light sensitivity, or otherwise known as the ISO, the lens itself is only adjustable by hand. Software cannot control it without extreme amounts of engineering and precision to make it controllable by software. So for this application, we're just going to be setting it and forgetting it, to put it simply. And this camera module is not rated for external conditions by itself, so it will require weather protection in the form of a casing. And that will be also discussed later on in the PowerPoint as well. To continue, the motors we're going to be using for this application, for the pan and tilt controls for the camera itself. For the pan, we're going to be using a 20 kilogram inch torque rating servo motor. They're both digital. The bottom one for the panning or the horizontal motion will have 270 degrees of range of motion, and the tilting servo, which will control the vertical movement of the camera, will also have the same torque rating, but it will only have 180 degrees range of motion because there's no point in going further than 180 degrees with a vertical camera. These work off of pulse width modulation, so you send it a signal, and the duty cycle of that signal, or pretty much how long it's on for, or how long it's high at 5 volts, it will tell you exactly, or it'll tell the servo what position to turn to due to its internal encoder, internal potentiometer, and feedback system. Because servos are all in one, they're better compared to stepper motors, where stepper motors are more open loop control. Servos are more closed loop control, where you can actually tell it exactly where you want it to go, and it will use internal feedback and PID and fuzzy logic control to get to the point where you want it to be. So for these servos, they both have a 500 to 2500 microsecond duty cycle range. If you turn that into a number that we usually use, that is half to 2.5 milliseconds. And so at 1,000 microseconds, you'll be at a position of 0 degrees. At 1,500 microseconds, you'll be at half the maximum angle. So for the panning servo, that'll be 135 degrees. And for the tilting servo, that'll be 90 degrees. And you can see that in this chart off to the side, underneath the picture, the example of the servo. That's kind of the chart of how the pulse width modulation breaks down and how it's used by the servo itself. And at 2,500 microseconds, you'll get the max angle, so 270 and 180 respectively. With this, however, there is a 3 microsecond deadband, which if you use an Xbox controller before, that's kind of like the dead zone settings. It is a limit on how much input it takes for it to actually respond respond to a change. So this will limit minute changes, and that I'll give you the more numbers on that in the next couple of slides. But it has a major implication on how precise these servos can be. And so these servos also, the power ranges for both of them will be anywhere between 7.5 and 15 watts of power at 5 volts and 1.5 milliamps to 2.2 amps. The 2.2 amps comes from the locked rotor current. That is the worst case scenario. It is pretty much another way to state it for people who are familiar with it is inrush current, because when you start a motor up, it pulls a lot of current to get stuff started, which is why, if you didn't know, your fan blades also do the same thing. Pretty cool tidbit. But these servos will also attach to pan and tilt the camera mount, and this will help orient the camera in the correct orientation that it needs to pick up the image of the drone, and also track it across the sky as it's attempting to capture the image. But to move on, we have a system schematic here that I've designed. So if you see, we have the Raspberry Pi itself right here in the center, and to the bottom of it, you have rails coming in from the power system, 5 volts and ground respectively. And for the USB-C cable, it is considered a bust wire, which is why you see the slashes here and also in the USB 3.0, because there's multiple wires within a USB-C connection. The Raspberry Pi needs C connection in order to actually power itself and operate. So we have to strip and terminate the USB-C properly for the power to be properly delivered to the Raspberry Pi. And the Raspberry Pi will actually specifies 15 watts of power. So that'll be about, at 5 volts, that is roughly 3 amps. So that should be more than enough for the Raspberry Pi to operate. It won't actually use all that current, but that's just for worst case scenarios. For the stripping and termination, we will also follow the standards for proper termination and shock protections. And we'll get to that when we start getting into actual construction. For the servos themselves, I've designated servo 0 as the panning servo, or the 270-degree servo. It is connected to GPIO pin 12, which is also pin 32 of the entire microprocessor board, and is on PWM pin 0. So the Raspberry Pi, it has 16 programmable pins, but only a certain number of them are dedicated solely to hardware PWM. And for motors, we want more precision, so we have to use those PWM pins to ensure that we have our correct angles. So for the panning servo, I have that on PWM 0. And for the servo 1, which is the tilting servo at 180 degrees, that input is also going to be on PWM 1, or pin 33, or GPIO pin 13. And so these servos come with 3 cables, or a 3 input cable. It has a positive voltage, a ground, and a pulse width modulation signal cable. For the power, we're going to terminate that into the incoming power. We are not going to go through the board, because if it pulls too much current, we will fry the board completely and we will tank the entire system. So the servos have to be grounded to the actual power source and not the Raspberry Pi. And there are some concerns with disruption due to the EMF generated by the servo motor, but servo motors usually have, or sorry, in this case, these servo motors do have internal back EMF protections, so we don't have to worry as much about any kind of current coming back through the line and potentially browning out or decreasing the voltage gap of our Raspberry Pi and causing it to no longer operate properly. So for the camera itself, it's going to be powered and controlled through the USB 3.0 connection. So the Raspberry Pi comes with 2 USB 2.0 and 2 USB 3.0 connections. We're going to be using one of the USB 3.0 connections, which is why the cable is a bit off to the right instead of centered. It's depicting that it's going to be on the very bottom USB 3.0 terminal. And so within these wires, there's 4 wires itself. There's the data wire, the communication wire, the voltage, and the ground. And so we need to be able to supply 3/4 of a watt to this camera. And the Raspberry Pi, there's a typo there, it says Arduino, I'm supposed to say Raspberry Pi, but the Raspberry Pi can handle applying that much power at 5 volts very easily. It has no trouble with it whatsoever. So moving on to some more specifications, the processor must control all the components with minimal disruption. So that includes both the servos and servos, cameras, and the software itself. So that includes wireless transmissions, internal calculations, and what have you. And it will also have to be capable of sending a status alert signal, and that'll be detailed in the camera software system presented a little bit later. For the camera itself, it's needed to capture images from long ranges. We're looking at anywhere between 10 and 100 plus meters because with contiguous campus coverage, the longest straight line that I was able to calculate was roughly 600 meters or 1,400 feet. And we're probably not going to get to that maximum range. So we're going to go ahead and constrain it down to at least 100 meters, just so we can get pretty good range with that. That's roughly like 3 football fields. So we can get pretty good range with that and still be within our camera parameters. But the camera will not take into consideration light levels, physical or environmental obstructions. We're just going to take a picture wherever the drone is, and we're going to send it into the database, and it's going to parse it through there. The zoom, focus, and ISO, as I said earlier, will be set when the system is installed after some troubleshooting, and we will not be changing it after the install unless it is being moved or maintenance in any other way. And the camera must capture images in a RAW or PNG format to preserve the image quality, so that when we send it through the database, we don't lose much to compression, and we can preserve as much quality as possible. For the motors themselves, they're going to be dependent on signals fed by the camera software system. And these servos, like I said earlier, have a limit on their precision based on the pulse width modulation range. And so to this equation to the right, the change in the minimum change in the angle will be the max angle minus the minimum angle. So in this case, either 270 or 180 minus 0 over the maximum time and the minimum time for your PWM range. So that in this case, for both motors, is going to be 2,500 minus 500 microseconds. Once you get that ratio, you have degrees per microsecond. And to get that into a minimum change that the motor can see, you multiply that times your deadband rate plus 1. So, or plus 1 microsecond. So with that, the deadband range, it is less than or equal to 3. So to avoid any kind of errors with any potential errors when it comes to calculations or any inconsistencies in the manufacturer's documents, we're going to go ahead and add 1. Just assume that the deadband is 4 seconds. And that way we can ensure that the servo will not jump, jitter, or stutter. So with that, we will end up having a minimum change. So the minimum resolution that the motor will be able to see. For the 180, we are looking at 0.36 of a degree. And for the 270, we are looking at 0.56 of a degree, so just over half. That will constrain our precision based on the focal length itself. And more math and more discovery will have to be done on that because, again, we don't have the manufacturer specs for the focal length, or sorry, not focal length, the field of view. So to get that, we need to actually do a little math, do a little some well-educated guesses based on other camera modules, and see what we are looking at in terms of accuracy as you change your motor position. So the current status of this system is that it is roughly 80% complete. The system needs to be, I need to find the NEMA rated enclosure for both the microprocessor and the camera. Additional justifications and feedback for plan metrics and constraints are needed. We have all gotten feedback back as of yesterday, May the 1st. So it was a little bit tight in terms of trying to get a sign off. So we have not gotten sign offs for any of our systems. So I'll also need a final review and a system sign off with the project supervisor. And once that's signed off, I can finalize my bill of materials and order my parts for this part of the system. So in terms of future work, to sum it up, pretty much work on all of that I just mentioned. And the goal is to have this all completed by the first week of the fall 24 semester. That way I can hit the ground running and we can get started on construction. Thank you for your time, and I'll pass it on to the next person.
Austin Williams, and I will be covering the receiver power system. So getting started, obviously the functionality of a power subsystem is to supply the power required for that receiver system that we're powering. All the components want to be adequately powered. And for this case, it'd be 5 volts to the ESP Nano 32 of the receiver system. Moving on to constraints, the system shall be designed to minimize future maintenance, which is a broader implication just to make things easier for the implementation of the project, but also it's a big emphasis of Dr. Austin, the supervisor, for the entire project. For number 2, we would be complying with ASTM B258 standard and that's just over the wire gauges and current through a wire. You want to comply to that for safety of your system. You want to avoid overheating, short circuit, and fires even. And then also for the next one, we will be weather resistant with an IP67 rating. We're going to be using a NEMA box for that, and that's just going to cover rain, snow, dust, wind, and UV. And that also has an environmental impact. If there's any sort of damage to the battery in the module that we'll be using, that will keep that contained as well and not getting that corrosive material where it shouldn't be. And then number 4 is pretty obvious. The system shall be able to supply enough power to the receiver system. Obviously, you want full functionality and you need power for that. And moving on to the schematic here, this is a very bare bones schematic showing that we'll be using solar energy to charge the lithium ion battery in the module there. And then from that module, we'll be using USB-C connection to power the ESP32. And any additional modules can be powered from the Nano itself. And this system has not been signed off yet. Both the power subsystems lack the hardware systems. And Dr. Austin said we can't be signed off until the system we're powering is actually being signed off. So moving on to the camera power, this is very similar here as far as standards go, but the functionality for this one is obviously to power the components in the camera subsystem. And it's going to supply 5 volts to actually every component. Same standards apply for the IP67 and the ASTM there. And we also just be powering the camera system and all of its components. And this table here shows the power requirements for the camera subsystem. As stated, it was all 5 volts. And we're just going to see, you can take a look at the total wattages and the currents that we're going to be seeing in this system. And then moving on to the schematic here, this one is also just a basic connection because of the lag of the power subsystems that Dr. Austin has stated. But we're going to be transforming wall power with a 5 volt output transformer. That transformer is 100 watts and 20 amps, which is a bit overkill, but we would rather have too much than not enough in that scenario. And the price difference is not really a consideration to be taken in case because it's just a few dollars for that extra wattage. But we will be powering a Raspberry Pi, the camera, and the motors all with 5 volts. And as mentioned before, this subsystem is not signed off because the receiver system and the camera hardware system have not been signed off yet. And so that has been a constraint from Dr. Austin just on the total design of the system.
Hi, my name is Meredith Nye, and I'm going to be presenting the camera software system. This was my system that I designed as part of the drone tracker project, and it controls the camera hardware system. The functionality of this system is very much intertwined with all of the other systems in this project. And it's important to note that this is true across the board for our project. So first off, the camera software system will use the data acquired by the receiver to generate signals that will control the system's motor servos and camera activation status. So the database system will collect information, the RID data from the drone. It will collect that information that the receiver received, and it will send it to the camera system. My system will collect that information and use it to calculate how the motor should move and whether the camera should take a picture. Once the image is acquired, this system will format it according to the constraints and send it back to the database so that the database can send it to the website so that the website can display it to the tech police. The system will also send an alert signal if there are detected errors. This was added into the functionality because maintainability was something important to this team and important to the supervisors and stakeholders in this project. So the alert signal, our hope as a team is that it will allow the tech police to maintain the functionality of this system, because otherwise they would not be able to know whether something's going wrong or not. There are 6 constraints for this system. The first constraint is that the system is not expected to capture an image of the UAS, the unmanned aircraft system, or control station if light levels and/or obstructions hinder the camera's view of either of those things. This was important because the system will not be complex enough to determine whether the UAS or control station is obstructed from the view of the camera. It will take a picture regardless of light levels, regardless of these environmental factors. So this constraint is saying that the team cannot be held liable for not capturing an image of the UAS because the system is not complex enough for that. The second constraint is from the tech police. They prefer a picture of the UAS control station over a picture of the UAS unless the UAS enters a high alert area. So this constraint talks about how the system will prioritize capturing a picture of the control station unless the UAS is in a high alert area. We'll know if it's in a high alert area based off of data sent to the system by the database. The third constraint is discussing location prediction. Location prediction will be performed if the UAS or control station is moving in a straight line, but it's not required if the UAS or control station is moving in any other trajectory. Number 4 is talking about how we will determine whether or not the UAS is moving in a straight line. So 3 and 4 are intertwined in a way. It's important that the third constraint exists because if the UAS or control station, the object that we're tracking, is not moving in a straight line, the location prediction will not be good enough to predict. It will not be accurate in its prediction. So we place this constraint so that the system will only be required to predict when it is moving in a straight line. And the straight line will be determined within a 5% error margin, and it will have to use at least 3 data points because 2 data points will not be enough information to determine whether the motion is straight line. Moving on, the 5th constraint, the system shall output the picture taken to the database as either a raw file or PNG. Raw files and PNGs will help maintain the quality of the image captured. That is why this constraint was important. And finally, the last constraint is a standard. The system shall communicate with the database system according to IEEE standards and Tennessee Tech policy. The standards and policies that we're following will help define the security levels for the data we're sending through Tech Wi-Fi, and it will also decrease internet traffic and ensure appropriate data transfer rates. And the standard as listed is 802.11, and the Tennessee Tech policy is 856. Now, after constraints is the design or flowchart in this case, since the system is only software. And the flowchart is as follows. I had to split it into 2 different parts, but they should be connected as if it was one entire vertical flowchart. But the flowchart will start, the data will arrive to the database. I'm going to store the data and define variables. Next, this section right here is following constraint number 2. So the code will allow a UAS in a high alert area to take precedence over a control station location, but it will attempt pictures of the control station location if the UAS is not flying in a high alert area. So that's directly from constraint 2, and that's what this block is concerned with. Now, if neither of these things are true, I'm going to go back to the start, wait for new data to arrive. So once we've determined the information that we've been given, we'll move on to here, where we're determining whether a picture should be taken. So this block of code right here is concerned with 2 factors. The first factor is the UAS or control station close enough to the camera to take a quality picture? And then the second is, does the system need to take another picture? And so those 2 things should be accounted for when determining whether a picture should be taken. And specifically, whether the UAS or control station is close enough will depend on the camera hardware system and what type of lens the camera has, what the field of view is, what the settings are, things like that. This block right here is according to constraint 3 and 4. So it's about the location prediction. It's asking, is the UAS or control station moving in a straight line? And if it is, the location will be predicted according to calculations that I will go over in the analysis section. But if it's not, then it will not predict the location. Regardless of whether the location is predicted or not, both of these lines will end up back at computing the pointing angles and position of the camera and positioning the camera to take a picture. So if it's moving in a straight line, it will predict the location and use that to compute the pointing angles. If not, then we're going to go straight to computing the pointing angles. And it should be noted that this is all under yes, a picture should be taken. So after the pointing angles are computed, which we'll go over in the analysis section how that will be done, a picture should be taken, sending the pictures to the database according to constraint 5. Once the picture is sent, the system should ask itself, is there a malfunction? Is there an error? And if there's an error, an alert will be sent. An important note for this flow chart is that this is not a final design. The project supervisor has recommended that the structure of the code be event-driven instead of a polling system, as is shown in the flowchart. But the basis of the flowchart is still useful to describe what the system should do and how it might go about doing that. For an event-driven system, the flowchart will be parsed into events that take place, such as the data arriving into the system, the power levels becoming low, or the drone being close enough to take a picture. Then the system would execute the appropriate functions, as we kind of described in the flowchart. It will execute those functions when each event takes place, not in a flow structure. And the event-driven system is important to implement because it will allow for better code modularity, troubleshooting, and clarity. So as I mentioned in the flowchart section, there will be camera pointing angles computed if a picture needs to be taken. The math for these camera pointing angles are as follows. There will be a horizontal pointing angle and a vertical pointing angle. The horizontal pointing angle will depend on the longitude and latitude of the camera and the longitude and latitude of the object, which I have defined as the UAS in this particular diagram. It will depend on those 2 things to determine the X distance and Y distance. And from those distances, using trigonometry, we can determine the angle that the camera must point in order to be facing the object that it wants to face, in this case, the UAS. The vertical pointing angle is very similar. The X and Y coordinates will be used to find the L coordinate here, which is this long portion of the triangle. And once we've determined L, which is the square root of x squared plus y squared, according to trigonometry, then theta 2 can be determined using the same formula as before with the inverse tangent. For the predicting the object location, these are the calculations given. Determining straight line motion over 3 points according to our constraints, so that we must have 3 points. Those points are defined as x1, y1, x2, y2, x3, y3, as given P1, P2, and P3. We'll find the slope values between P1 and P2. Then we'll find the slope values between P2 and P3, and those are given as M1 and M2, both slope values. Now, if the ratio of those, so M1 over M2, if those slopes, now, if the slopes are the same, that's indicating that the drone is traveling in a straight line over a span of 3 points. So the ratio of those, if it's exactly in a straight line, they should be 1, but that's very unlikely for it to be that precise. So I chose 5% error margins is accurate enough for the system. So if the ratio is between 0.95 and 1.05, then straight line of motion exists with 5% error margins. Now, if straight line motion exists, then we can predict the future location. And predicting the future location based on the velocities, the velocity value of the UAS or control station given by the RID data that's transmitted to our system through the database. Using those velocities, we can create a ratio of those and multiply those ratios by the difference traveled, and then add that to the last location that we knew about the drone. We can use that to create a predicted location here. Now, here are some system conclusions. First of all, this system's design is still under review. It has been reviewed multiple times, but it is still not perfect. As I mentioned in the flow chart, design changes are being made, but this is the overall scope from where I am now. This system will depend heavily on the camera hardware system. And there's no bill of materials due to it being a solely software-based system. So no materials will be ordered, but the system is incomplete in its design. And the section references are as follows.
Hello. Today I will be talking about the database subsystem, its functionality and detailed design, and its status. So for the functionality, this subsystem will receive a data package from either the receiver or camera system. Then the system will unpack the data and store it inside a database. Okay. Once the database application unpack the data package, it will extract the relative information from the RID signal, which includes the drone ID, and the drone location and the control station location. Then it will check for the corresponding drone ID and see if a authorized access is given or not. If no authorized access is given, then it will request user for an operation access that will be sent to the website system. If the operation access is denied by the user, then, or if the operation access is denied by the user and the drone is detected inside a priority zone, then the database will forward like the following information to the camera system, which includes the drone location and the control station location. And for the database, there's two components, hardware and software. For the hardware part, it will be using the Raspberry Pi, which is have few components, a M.2 SSD, which is to use it for storage that stored all the data that's extracted from the drone, the RID signal received it from the receiver system, and to connect the M.2 SSD to the Raspberry Pi, NVMe to PCIe adapter is used. And inside the PCIe adapter, NVMe to PCIe adapter, you have few pins that provide the power needed and input and output for the M.2 to function. And the pin is from 1 to 10, and the detail of the pin is shown on the following. And the Raspberry Pi will need a case which to use as a security reason that prevent outside access from interference with the hardware of the device. And the Pi and the Raspberry Pi will have a cooling device inside of it that keep the device under 85 degrees Celsius. And a external power supply is needed that provide 5 volt to empower the Raspberry Pi. And on the right corner here is that the Raspberry Pi will be using a Ethernet port to access the data transfer application, which sends and receives the data package. And for the software side of the database subsystem, it will use a Raspbian, which is a 32-bit system OS, to code the Raspberry Pi to obtain the functionality we needed. And the database implementation will be using MySQL, and the requirement on it will store the data for a minimum of 90 days. And let users select the maximum day it was to hold the data. And for the data transfer application, it will be implemented either in C, C/C++, or Python to send and receive data application. And first of all, receiving the application for the RID signal, we will a little bit more detail, which include the drone ID and drone location and control station. For the location, it includes the longitude and latitude and the altitude of the whereabouts of the drone and the control station. And to send the data to the camera system, which will only include the drone location and the control station. And when the camera track down the position either of the drone location of the control station, then I will receive an input from the camera system, which includes a bunch of raw files or PNG. And by subsystem conclusion concludes this, the system does not yet meet the sign-off requirement as of the May 1st of 2024. And there are some minor changes need to be made to the detail design, which include the schematic details for hardware, and part of constraint need to be explained in more detail or need to be changed to fit the design. And more detail and analyze explanation on hardware and software need to be done.
I'm Abraham Perkins, and I'm going to be talking a little bit about the website subsystem for the drone tracker project. So the website should allow a user to look at the data that we've gathered using the other subsystems. website is going to present the data gathered in a way that is clear and concise to the user. In this scenario, our user is a campus police dispatcher. So they specifically requested when we met with them that our data be showcased on a website and not like a mobile application, so that officers in the field didn't have to carry their cell phones with them. They could just get it through their walkie-talkie or their earpiece and be able to just go get the drone. It's going to overlay the drones detected onto a map of campus with markers presented everywhere that a drone is detected. But it's not going to cover anywhere that's off the contiguous campus. So no Heidelberg's Pavilion, no Appalachian Center for Craft, just the main campus, really. The website's also going to give our user the ability to designate specific drones for certain things. So you can classify them. I talk a little bit about it later. But there's two main classifications. There's a clear, and there's like an elevated safety concern. The website's also going to let the user input search information. So you'll be able to search by serial number, by time. I guess you can search by latitude, longitude, but that doesn't seem very practical. To create the actual web page, we're going to mix a little bit of HTML and CSS to get all the styling and the actual sections of the web page right. And then we're going to use JavaScript to handle the interactivity of the website. So Google has a Maps JavaScript API that you get $200 worth of access to for free. We've run the numbers with like heavy use of our subsystem. We're maybe cracking half of that. So they'll still have half of the budget left over. It's not a concern. But this API is going to be called a couple different times. Mainly, it will be called when the web page is loaded to instantiate a new map of campus. And then anytime we receive a new drone detection, it's going to be placed a marker on the map with the drone information. And the control station will also get a marker. Auxiliary drone statuses, like I said earlier, there's a cleared status. So the website is going to allow the user to go in and set a drone as clear so that an alert is not generated whenever that drone is detected by our system. You will need the serial number to do so, because it's the only way that we can tether something to the drone it's the only information we'll be able to get from the RID that we can tether to a specific drone. There's also an elevated status, which it'll be attached to the drone whenever a drone flies into a designated area. So our system will allow the campus police to go in and select certain areas as special high priority areas, like dorm rooms, sporting events. And what that means is that you can go in, and if a drone flies through that area, it will issue a higher priority alert, and it'll show up top of the list, different color on the map. They'll know it's there. This is done because when we met with campus police, they really seemed concerned about drones at like football games and looking through windows at dorms, and so we figured this would be a good way to set those special cases apart. That gets into a breach of privacy kind of concern, because while this project really aims to increase campus security, we're taking a lot of data that we don't really need to. In the eyes of the public, it's just there. We've looked into the data retention policies, and we're going to make sure that the data only stays in our database for as long as we have to keep it in there. But We don't want to be seen as some big entity that's just taking all this free data and storing it. We're also concerned a little bit about whether or not the web page would work on every browser, on every device. And so we've been told about validators that have been created by the World Wide Web Consortium. And you can run your page through that and it will tell you, hey, you have this issue here, this issue here. And so you can go back in, fix those issues, and then when it gets validated, you know that it will work. Subsystem status. Right now, a sign-off has not been achieved. We turned in the pull request. It finally got looked at yesterday, and we got good feedback from it. And so with changes based on the feedback we received, we think the subsystem will be checked off very soon. And the parts ordered, like I said earlier, the only part that we need for the subsystem is a Raspberry Pi, which is being purchased by the database subsystem. And so there are no parts that need to be ordered for this subsystem that are specific to the subsystem. That being said, the Raspberry Pi has not been ordered yet, as the database has not been signed off. Thank you.
Hi, I'm Meredith again. I'm going to talk about the timeline. I created this Gantt chart earlier in the semester as part of the project proposal. And if you look at the Gantt chart, you can see that I placed some of the big assignments that I could find on iLearn that the team needed to meet, some of the presentations that we would be completing. See, our final presentation is right here in blue. That's what this is. I have the breaks over the entire course of the next year. So this big pink line is summer break. And then the different systems, the power system, receiver system, database, website, camera system. And I created different benchmarks under each of those systems and how long they would take. And then the timeline of the system's design, how each system would depend on each other's, everyone else's system in terms of completion and what that might look like. So should be noted that none of our systems designs have been completed and no materials have been ordered. Now, in this timeline here, I anticipated that that would have been completed. That has not been completed. And I would say the reason for that is that we are busy people and the project as a whole did not require enough urgency. So I think leadership has a lot to do with that. Leadership, we didn't push for getting that completed by the end of the semester. We felt comfortable with the amount of work that we completed. But I'd also say has a lot to do with the amount of meetings that we had per semester. So increasing the number of meetings that we have and increasing the meetings that we have with our supervisor may help with our productivity. But we did not meet those goals, those sign-off goals that we had. But the good news is that according to our Gantt chart that I created, there will be still design portions being completed next semester during the first 2 weeks. So there is still time for us to stay applicable to the Gantt chart. Additionally, something that may change is the work that our team